Viděl jsi tady tu nabíječku včera? Já jsem ji nechal zapichlou, víš, tady v tom stole. Na Meka. Tak se pak když tak zeptáme. Okay, so may I again ask you for attention. We are going to have the second lecture today, provided by Heiko. So thank you very much for coming, and we are all looking forward to your talk. So I think most of the students are here already, some are coming soon, so if you will start slowly with the introduction, they will hear it outside and they will come. Okay. Thank you.
Yeah, thank you very much also for inviting me and for the whole organization. I guess it was horribly much work and still is, but you're doing a fantastic job, and actually thank you to the whole team. It's really great. Everything is perfectly organized, so thank you very much. And yeah, it's great to be here. Yeah, these old lecture rooms are also really special. So it reminds me a bit of my time when I was in Graz, that's Austria. So maybe that's not just a coincidence that there it looks similar, but I don't want to say too much. So my name is Heiko Hamann. I'm from the University of Lübeck in Germany. My background is, well, swarm robotics, also swarm intelligence, some evolutionary robotics, so that's the application of evolutionary algorithms to robotics. Quite some modeling, so I've started more on the theoretical side, and then over time I moved a bit more towards applications, or at least working with actual real robots. So the plan for today, well, for this afternoon from my side, is we will have these two little time slots. So I'm trying to help you here. So you must be very, very tired, right? So this is after half of the week. It's warm, and you had already so many lectures. So I will try to be short. I will try to entertain you. I mean, that's a trade-off, right? So because I also want you to learn something, but a precondition is that you are paying attention. So I try hard to entertain you, but that also means I have rarely any equations, so that's kind of embarrassing after all these other talks. I hope you still take me seriously. So this is real science. It's only I don't give you the details. But you can always read the papers at home, you know. So I'm trying to inspire you here. And then about the questions, you can feel free to ask questions at any time. If I don't see your hand, just shout loud, because I'm getting old, I don't hear everything. And then, but only quick questions, and then in the end, hopefully we still have some time to have a longer discussion. And then also, well, I wasn't here on Monday, for example, so there's a chance that there will be some repetition, right? So this is more like a general overview, so apologies for that. Maybe you shouldn't shut down your mind in that moment when you see that's what we talked about before. Maybe you can think about it, what you already know, and how does it relate to how I'm presenting it. So just quickly about myself. So these are the different places I've been. So Stuttgart, then Corvallis, Oregon, which is not on the map because then we would have zoomed out a lot and you wouldn't see anything anymore. Also, I guess Google Maps would have had a hard time to find a route. And then Karlsruhe, Graz, so you know, these mostly German-speaking countries, and then Paderborn, and all the way up in the very north of Germany. Now I'm in Lübeck, which is actually just less than 1 hour drive from Hamburg. And I'm always saying, if Germans are asked, what is the nicest city of Germany, they say Hamburg. I have some idea why, but on a nice sunny weekend, these Hamburgers drive to Lübeck at the beach to have a nice time, right? So maybe it's worth a trip. Okay. And then, speaking of disclaimers, so another disclaimer is this one. I'm sorry. So this is a completely drone-free talk. Sorry. I guess you're very much into drones. I'm not. I actually have a strong opinion about drones, so later maybe I can mention a bit more about that. You know, I'm also trying to be provoking, and feel free to hate me. Then when you talk about swarms and swarm robotics, the public perception is a bit special. Maybe it's because of that, right? So, like if I talk to random people on the street, which I never do, then they would wonder, like, yeah, well, aren't you building the new Terminator, and we all will die? And this is probably why. I mean, most of them are beautiful pieces of art. So if you read, for example, Stanislav Lem, that's really high literature. But what's common, I mean, I tried to visualize that by putting on all these skulls here. So people see it as a threat, and it's also the danger of the new, right? And but there are all these nice things and beautiful things we could do with swarms. So I'm trying to convince not just you, I guess you believe me, but all these other people that this is actually really useful and interesting stuff. By the way, so kill decision, Daniel Serrano, anyone knows that? Have you read? Okay. So actually, Marco Dorigo is even mentioned in there. So this is the big guy of swarm robotics, and he mentions the name and he discusses his work, and wow, well, that's crazy, right? But public literature or pop culture, if you like. Okay, so I've also written a book. I'm sorry for this kind of marketing thing, but it somehow relates to the subject. So this was published last year. The price is ridiculously high, sorry about that, but maybe you can find some PDF online somewhere, or you tell your boss to buy it, or the next library, something like that. So I will come back to that. So but I will not just revolve just around that. Okay, so talking about swarms, and well, you've seen swarms in this week before, I think. So this is just one random video. That's actually a drone, right? But you don't see it. So that's nice technology to take this video. And these are sheep, right? So often we talk about ants and social insects, but also sometimes mammals, like sheep, can show some kind of swarm behavior. I mean, they don't really feel well, so this is like a flight behavior, so they're running around, they're in stress right now, but okay, still it's some swarm behavior. And when you look at that, I mean, again, I'm coming from modeling, right? So when I look at that, I don't see sheep. I see a liquid, right? So then I'm starting to think about how could you model that, because this is not really individual sheep showing some complex behavior. This is more like molecules being pushed around, and then you have like floating sheep, right? So that's kind of the mood of this talk, maybe. And I'm not going to introduce swarm robotics again and define all the different properties. So probably you have seen and heard that before. So there's usually the idea that this is a decentralized system. Also this one actually is. Then it's asynchronous, right? There's no global clock that you can check. Usually if you want to have a synchronized swarm, you have to synchronize it by yourself using some algorithm. Very often we talk about homogeneous swarms. So is that really homogeneous? Well, not really, right? Because these are hopefully not all clones. It's not the Dolly swarm. And so it can also be heterogeneous. Also in swarm robotics, we start to look more into heterogeneous swarms. Usually the idea is to do that in terms of hardware, but you can also have heterogeneous software, right? So different controllers on maybe hardware-wise identical robots, so that might also be interesting. And then usually you say you have local information, only local communication. Why would you do that? Why do you restrict yourself? It's just making things very, very hard. Well, you get something from it because then your system scales well, and maybe it's also robust because of quite some redundancy, but that's actually kind of a lie. So it's not always true, and you have to really look into your system whether it's really robust. So speaking about the individual this is also just a very rough idea here. So of course you can, oh, now I have to be careful. You can cut open heads, but now I'm speaking about the upper part of the image. So you can cut open an ant and count the neurons, right? And if you want to do this purely quantitative thing, which is not always a good idea, so if you think about these singularity people, they just count neurons and then they say soon we have human intelligence. So you can really do stupid things by arguing just quantitatively. But the idea is roughly clear, right? So an ant brain is actually magnitude smaller than what you have. So in a human being, so the factor is like 100,000 times more. So you should be careful in not saying, well, then obviously ants are stupid animals, then the next biologist will hit you. So you have to be a bit careful because we can't really build ants, right? So we can build small robots, but building ants is still a problem. But anyway, so these are rather simple animals and they still achieve quite something. And then another thing that I don't really go into details with because I'm assuming that you know already quite a bit about it. So there's the concept of reactive behavior, right? So if you want to keep your controller simple, if you want to have rather simple robots, maybe reactive behaviors is an opportunity. So there's a whole field called behavior-based robotics. Maybe you have heard that at some time. And then the idea here is that you have rather simple robots. No memory is maybe saying it a bit extreme, so you could have some memory, but maybe not so much. Then I'm not really talking about planning here, so you've seen already quite a bit about that. So we usually try to, well, kind of avoid that. I've mentioned decentralized local information. And then have you heard about the work of Gray Walter? Maybe, so this is the guy you see here in the video, and this is quite amazing, right? So he worked on that in the late 40s and then published it in 1950, which is one of the first reported works where you have an actual mobile robot operating based on a reactive scheme. And what you see here also in this image here on the left is how can you still implement some kind of phototaxis in a robot that has just one sensor. Oh, that's the wind, okay. Just one sensor to go towards the light, right? And the idea is you go in spirals, and then you actually change the radius depending on the light value that you measure. So do you have any idea? Let's say if the light gets darker, what you perceive as the robot, should you increase or decrease the radius? Huh? Decrease? Yeah, I think you can kind of see it here even in this graph, right? So this is a wide radius, this is a small one, and that, well, plus some magic numbers, right? And then you get the desired behavior. Or if you open the AI Bible, Russell and Norvig, then you don't have to read much of these 1,000 pages. Like on page 50, you will find simple reflex agents, which is the model over here, and this is kind of what we're doing here. Okay, but this is all kind of boring, right? You've heard about that before. So let's look into a bit more specific issues of swarm robotics. And this is an image I choose to try to explain that we have always these two different levels, micro and macro, so microscopic level, macroscopic level. And the microscopic level is the level of the individual. Like if you take one individual ant from here and think about what is she doing, what does she know, and actually she doesn't know much and she's not doing much. So there must be some reactive control here, most likely. Biologists don't really know much. But if you would interview one of these ants, what we can't do, then she would probably answer something like, well, if you ask, what are you doing? She would say, well, I'm just grabbing this person in front of me because I feel like, right? And she would not talk about, well, we are weaver ants and we want to build a new house and this other leaf was too far away, but we want to pull them together. That's the global view, the macroscopic view. They don't know that. So when you look at this picture, you already know much, much more about what they're doing than each individual in this picture, right? So that's really important, and it's both a blessing and a curse for swarm robotics, because On the one hand, we hope that we have macroscopically defined complex tasks that we can solve with simple robots, but the problem is how do you break it down from macro to micro, because in the end you have to produce some C code that you can upload to your robot, and then the robot will not have all the information available. So how do you really do that? So this is definitely one of the main challenges of the field, and this is just another photo where I try to show this like self-referential feature of this micro-macro problem. So you have a task for the whole swarm, they should behave in a certain way, and then each individual puts a little part into that, but from a very, very local view. And one more concept about that. So speaking about the right half of this slide, in astronomy, like if you think about Johannes Kepler, he didn't ever look to the sky, right, because he was short-sighted. So he had to wait for Tycho Brahe to die to get his data. And anyway, so the idea was to look out there into the macro scale, right, and understand the big planetary systems and the large-scale systems. And then at some time someone invented the microscope, and they did the same thing to look into the small. And then now, well, we were born too late, right? So how can we still do something novel? Well, maybe somewhere in between there might be something new, especially the non-graspable, right? So there, if you look into interactions between bodies, between agents, so if you think of a network or a graph, then it's about the edges, if you like. So this is how systems interact with each other. That's actually the novel thing, and that's where you can still, maybe be the next Kepler, I don't know. But that's what we're doing, and that's where I think where we can still contribute on a large scale and in a useful way to science in the end. Okay, then this is just to remind you, probably you've seen some definitions of self-organization. This is a very important building block or a property of these systems. And then usually self-organization is defined in this way, so this kind of dangerous way of defining it, order from noise. So a physicist might not like that so much. But then how is it possible that you get like a more structured system out of nothing somehow? Well, if you put it that way, so it's an open system, so you put in energy and it's wasting energy, and then you have it away from thermal equilibrium, then it's actually possible, like physically possible, that you generate order or patterns or something. So obviously, we will always have systems that burn energy when we talk about swarm robotics, right? That's also very clear, especially if you work with drones that just run for 3 minutes or something. Then you have these feedbacks, and I will focus a little bit on that. So positive and negative feedback is what you usually define, and then fluctuations, which are just random events happening that actually help you to reinforce something and then build a pattern, multiple interactions, and this kind of difficult to define balance of exploitation and exploration. So let's look into the feedbacks. There's positive feedback, and again, I might bore you a bit here. You can't read really everything. So one example for a positive feedback system would be a market bubble. And what you see here is like the price index of the US housing market from a long time ago all the way till 2010 or so, and this not so small peak is from 2009. So you know a bit about economics, right? So usually prices are generated by supply and demand, but if you don't sell and buy houses on a daily basis, then there's also quite some trust in the system, and this is what happened back then, right? So there were investors, they bought houses, and then other investors thought like, oh, this is an interesting market, let's invest, prices increase, more investors invest, and at some time you have this bubble because you put more and more money into the system, and at some time someone tries to sell their house, and they find that no one is willing to pay this super blue sky price, and then everything breaks down, right? So with positive feedback, usually everything would explode. You have this accelerating system, like this snowball, but this planet has limited resources, what we just know too well, and at some time it will always stop. So there's this counterplay part, negative feedback, which is like from control theory, something like the centrifugal governor, that whenever you have some deviation, there's some kind of damping, and then you bring the system back to some equilibrium. So and that's something we will try to investigate also in the second talk later. We try to find that again in a swarm system that makes a collective decision. So if you remember that, you can score high on our surprise exam that we have later today. So, not really, but okay. So this is just some hardware from Swarm Robotics. I guess you might have seen some of that during this week already. So this is like the most iconic good old guy, the S-bot from the SwarmBot project of Marco Dorigo from Brussels. Then not sure if you've seen this guy. That's actually a real robot on the nail of an adult's thumb. Tiny, right? So it's like a footprint of 3 by 3 millimeters. It was also an EU project. The problem was it was not really fully functional in the end, but it could have been. So it has no battery, of course, highly efficient solar cells, and then like vibrating legs. So a little bit like the idea of the kilobot, only the kilobot is like 1 magnitude bigger. So maybe you've heard about the kilobot. So this one has a footprint of about a €2 coin. Not sure what it is in Kronen. And then this one has also these vibrating legs, and obviously it's just made for the lab, right? It's good for nothing, but you can show something in the lab. So Alice, this is from EPFL. Back then, it was difficult to get these small electric motors, so they had a deal with Swatch. So at some time, these Swatch watches were popular. So they got special electric motors from them and could build also a really small robot. And this is just one example of like one of the first legged swarm robots, the Spiderino from Klagenfurt in Austria. Just to give you some rough impression, but all these guys live in the lab, right? And that's kind of boring. So let's see whether there's also something else. So there's also some swarms outdoors. This would be from the EU project Subcultron, coordinated by Thomas Schmickel from Graz, Austria. They actually tried, well, to implement this swarm out there in the lagoon of Venice. That's a good idea, right? If you write a proposal, of course you have to try it in Venice, right? So making sure you make all these trips to Venice for 4 years. So they want to build like 100 of these like muzzles, so they can just go down to the ground, measure something, come back up, and then they have floating robots and also some robots that can actually really swim like a fish, if you like. Then this is from actually our institute, so we have some tradition of building underwater robots. It's kind of a swarm. It's only 3. We will get to that in a second. They are very expensive, so communication, localization underwater is really difficult. So then you have to buy expensive sonar modems and things. And this one is autonomous boats, and actually it was a swarm of boats from Anders Christensen. Back at that time, he was in Lisboa in Portugal. Now he's in Odense, Denmark. And that's really amazing work. So if you don't know it, you want to look into it. They actually also did this evolutionary swarm robotics concept. So they had methods of evolutionary computation to automatically produce controllers for these robots, and then tested them not really out in the ocean. So again, that was like in some kind of harbor, but it was outdoors, and that's really cool. And actually, if you ask me, this should be the way to go. So we want to kick our robots out of the lab. So get rid of these toys, get to real robots, and do some real stuff. So no drones on this slide, right? And I would argue that there's not really much work yet for like real swarms outdoors with drones, but feel free to fight me. And I would say it's no coincidence that you don't see like regular mobile robots outdoors yet, like on wheels or tracks or whatever. In German, we have a saying that translates somehow to the air has no beams, right? So there's no obstacles in the air, and similarly for the water. So maybe it's easier to deploy these robots in air or here in water to well, get rid of some of the big grand challenges of mobile robotics, right? So it's maybe not just a coincidence that you see quite some water on this slide. Okay, then one, like, I actually hate definitions, but of course you can ask this silly question about when is a swarm a swarm? How big does your swarm have to really be a swarm? And I would say there's no good answer to that, but you can look into the literature. Then there's this Benny paper, 2004, and he said somewhere in between 110 to the power of 23. Well, this is, if you heard about the Avogadro number, so this is from chemistry, and those who know me know that I hate chemists for no particular reason, but this is a strange number, right? Like, why would you put that there? And the idea is that you want to have a system that is already quite many, so you need special methods to analyze it, but it's still less than treating it just statistically, right? So a chemist doesn't really put down an ODE for each individual molecule. They speak of like whole concentrations and substances. So that's the idea where these weird numbers come from. I actually disagree. And then if you look into physics, speaking of Kepler again, but that was after his time, as far as I know, there's the three-body problem. So if you ask a mathematician or a physicist, when does it get complicated? And this is just Newtonian mechanics, gravitation, two big masses and one satellite moving between them, just subject to gravity. If you want to have a closed form mathematical description of that, for two bodies you can easily do that. For three it's already getting insanely difficult. So there's Poincaré who worked on that. Also a nice interesting story, whole books about that. Maybe you want to look that up. And the thing is, right now I think we just have like weird infinite series to write down like what is the expected trajectory, or if you ask like at time 1000, where will this object be? There's no easy solution. And then like also from the Greek side there's a contribution, so there's the Sorites paradox, asking a very similar stupid question, how many grains of sand are in one heap? And then if you're stupid enough to say a number, 1000, then the next question is, okay, so what's wrong with having only 999 pieces of grain in your heap, right? So that's of course the problem that we would also have here, so why not 99? And then you're trapped. So never give a number to that question. Okay, so speaking about the book, well, we will go through this. No, this is what you'll find there in the table of contents, which is open access. And we will pick some of these scenarios. So I will again give you just a little overview of different things. So again, I will stay superficial, but maybe I can still manage to inspire you a bit. So we start simple. One of the simplest tasks you can try to solve with a swarm is aggregation, and you can get some bio-inspiration, right? You're not alone. There are others trying to do the same thing. So honeybees would be the more typical example, but then you also have, for example, these ladybugs. If anyone has seen that, you can actually see that sometimes in nature if you dare to go out there. And I would say aggregation is like the hello world of swarm robotics, right? So it seems to be the simplest task. So let's go through this very quickly. So the task is minimizing distances between robots. And then, okay, the individual robot doesn't really know that. So for the individual robot, it's something like position yourself close to as many other robots as possible. So if you do that in a greedy way, you just see some other robots, you move towards them, and then you stay. What will you get? not one aggregation, right? What will it be? Yeah, many small clusters. Thank you for talking to me. Okay, so many small clusters, and that's not what we want. How can we solve that? Well, long story short, you have to explore it sometime, right? So if you are in a cluster of 3, well, maybe the swarm size is 3 and you're done, but you don't know, maybe. Let's say you don't know the swarm size, then maybe it's a small cluster, arguably. Then you should leave at some time and explore the world, and maybe you find a cluster with 5 and maybe some cluster with 15. So it's a competition between clusters, and the smaller ones should dissolve and the bigger ones should grow, right? Also, what if you don't have a bounded area, so you can actually get lost? So maybe it's not so simple overall, right? Okay, so that was aggregation. There's like the complement to aggregation, dispersion. So you can say this is the inverse. You want to maximize the distance to all the others to make it more interesting, because then you could just like explode the system if it's unbounded. To make it more interesting, you could say you should still stay connected, right? So for monitoring, it would be interesting to like occupy a certain defined bounded area, and then you still want to stay connected to maybe do some communication and propagate information through the swarm, like multi-hop communication. And then you could also ask about the distribution. So if you look into ecology, you can actually find some definitions. So they say, well, this could be dispersion. Many of you might disagree because it looks more like aggregation, right? So then you have like a random uniform distribution or an actual like uniform distribution. So, and the question is, what do you really want? And it's not that, well, for each of these you can actually make a case and argue that it's useful to disperse them like this. So maybe this is also not so easy to define. Okay, now a bit into more complex tasks. So there's task partitioning. I think it was mentioned during some of the last talks already. So this is one particular paper which is, I think, worth looking at, where they again used evolution, so it's kind of popular in this community for some reason to evolve behaviors. So what did they do? This is somehow bio-inspired, but if you don't want to look into that, you can also ignore that, but let's do it for a moment. So there are these leaf cutter ants, and they cut leaves maybe sometimes from something like grass or close to the ground, and sometimes from like bigger plants, like a tree maybe. And then the question is, well, you have these two tasks. One has, well, you should cut and you should carry it back to the nest. In this case, maybe you can do both at the same time, like you do both jobs. But in this case, cutting and bringing it back involves climbing up and down this tree, which is maybe a waste of energy. So then it might make sense not to be a generalist, but to distribute. We have some subpopulation cutting, one subpopulation carrying. And they didn't predefine that, so they evolved these behaviors and left the system to like discover this kind of task partitioning by themselves, and they actually observed that. So that was the nice result. So this is why you find this in PLOS computational biology, which is not too bad. And they implemented that, of course, with robots, as far as I know, not really in hardware, I guess. So this was simulation. But I might be wrong. And so you have this ramp instead of the tree, and then you don't want to have the robots like moving up and down all the time. And the question is like, what if I have a small swarm? What if I have a bigger swarm? What if the ramp is shorter or longer? And then you can look into all these situations when it's worth having subpopulations doing different jobs and when not. So I think that's actually like also intellectually an interesting problem and maybe worth looking into, so feel free to look it up. Another example that I want to mention here is task allocation solved with methods from multi-armed bandits. Anyone into this machine learning literature? So what is the multi-armed bandit problem? Yeah, you want to explain it quickly? exactly. Yeah, so it's this Las Vegas problem, right? So if you have been there, you know, well, this is a bit idealized, so I guess this is not how the machines work, but there's an underlying probability distribution of your payoff, and there's the assumption that some machines are worse than others. Well, in the end, you will always lose money, right? But okay. And you will get drunk, so tonight you get that cheaper. And so the problem is here to explore, and then at what time should you exploit the information you already have? So, yeah, like when do you want to like almost stop exploring and you just play this one machine you're convinced that it's actually giving you the best payoff, right? And you could even make the machines dynamic, so maybe this payoff also, like the underlying distribution, changes over time. Okay, so that's multi-armed bandits, but we talk about swarm robotics. So there's this paper from Pini and friends from 2012, where they applied that to task allocation. And this is, again, like a quite similar problem to what we've just seen. So there's a source, there's a nest, you have to transport stuff. But here you have two choices. You can go the long route, if you like, or you can go just here, and this is a cache. Not like what you have in your computer, but you can just drop stuff there, and then but you can't pass it, and then someone from the other side can pick it up and bring it to the nest. And here the question is, when should you do what, right? So at like first glance, it looks like, well, you should always put it in the cache, because that's shorter. But if everybody is doing that, then the cache is like overflowing, and then maybe it's worth going this way. And so what they did is they applied these equations, more or less, that you get for free from the machine learning community to saying, well, this is one bandit, right? Like playing this route, or playing this route, or playing this route. So you have basically three options to play. And the payoff is, of course, like the cost, like how long does it take you to do that? And there's an additional challenge here, which is different from the regular stuff, what these guys here in machine learning do, because this is actually some kind of self-referential. So if someone chooses to go this way, then actually the payoff for the next one to choose it is lower, right? Because now it's getting crowded. And I think that's really a very beautiful idea to just apply these methods here, and then you can play with it, like what if the robots communicate with each other and share some information and so on. So, well, hopefully some of you are interested now. Then you have different works on self-assembly. So very often in swarm robotics, it's not really self-assembly, it's more like an emulation of self-assembly, because people say in robotics usually they should physically attach to each other. But if you do it with these stupid little kilobots, then they don't really attach, they can't do that. So they just stop next to each other, and then we say, well, this is assembly. There's a nice science paper by the group of Radhika Nagpal from Harvard, where they famously aggregate 1,024 kilobots, that's where the name comes from, in these different shapes. Really nice work, has some drawbacks. So for example, all these 1,024 robots have to line up. So one after the other attaches to this shape. And you also have some gradient for localization. So they built their own like kind of indoor GPS. And there you have propagations of errors. So they worked hard on getting quite some precision there. And this is now, so I tried to keep it low, but this is some of the work of my group, IROS 2018. We tried to address a few things that they left for us. So what if you need a dynamic assembly? So it's not that you assemble it just once and then you're done and then never ever anybody moves anymore, but what if you react to some dynamic environment, here it's light, and you want to grow a structure into the light, but then at some time the light changes, or here we like cut off, so we grow trees if you like, and we cut off branches and then they should regrow. So it's a much more dynamic system for this, like some kind of adaptive self-assembly. Also, maybe not much more about that for now. Just one more comment. So the group of Radhika was actually addressing this problem. So here you see them lining up, right? So it's kind of not stupid, but it's kind of not satisfying fully if you have 1,000 robots and they have to line up, right? So, don't know, for English people, maybe it makes sense, like they line up for the bus, right? But, well, maybe you can do it in a better way and parallelize it. So and that's also great, like that's a strategy for you. Try to publish a science paper, and then later you bash it yourself, right? So you publish science in science, and then you publish many other papers how to do it in a better way. And so they did self-disassembly, yeah? And this is how it works, right? This looks faster. So you have to start like this. So instead of having a poor PhD student arranging 1,000 robots in a line, you have one poor PhD student aligning 1,000 robots in a square. So something new, right? And then they negotiate like who's part of the structure, who is not. I'm not going into details here. Please go to the paper. So this is Gauci, Dars 2016. So they find out, am I part of the structure, am I not? Then we have also these light beacons that actually have some meaning. So you can do phototaxis, anti-phototaxis, and then, yeah, so actually now the light switches, and all those that are not supposed to be part of that assembly now just leave, and you create these beautiful exploding robots pictures. And this is faster, but yeah, you know, is it really generally applicable? Well, we don't know. So much about assembly and disassembly. So this one I want to do really quickly because we will talk for 60 minutes about that a bit later if you're still awake. And collective decision making, if you ask me, is a really, really important scenario or task for swarm robots. So here you see some of our work. So this is not 1,000, but 100 kilobots, but at least they do something useful. And then here you have some epochs. They have to check like how many of these white and black tiles do we have. And here again we have kilobots doing some collective decision making in a dynamic environment. So the idea of collective decision making is you have several options. Maybe they come with different qualities, so you should have in the end a consensus on the best option. And then what if the features like here are distributed in space, so it's not just that one robot can go somewhere, explore, and okay, option A has quality 5. You actually have to explore the whole arena to find that out, so that's what we would call collective perception, which is maybe not the best term. And then this idea here would be, what if you have dynamic environments? So again, the quality of the options changes over time, and you have to make sure you don't end up in a deadlock and you can never reconsider. Everything on the macroscopic scale, right? It's this whole swarm making a decision and not just the individuals. Then one more example, that's also something that Antonio just showed us. He called it cooperative manipulation. I think it's pretty much the same. So this is also where you can get some bio-inspiration. So this is all ants. I'm particularly proud about this video because I took that myself a few weeks ago in Sweden. So you can imagine, you know, I did this little hike somewhere in the middle of nowhere in Sweden. And then I found this passenger bridge with ants having a trail there, and they were actually transporting stuff. And then, okay, the hike was 1 hour longer. And I really like it, so that's a lot of fun. And this is a random YouTube video where you have this funny behavior that they've really formed these long lines. Don't ask me. I mean, I've worked in Graz with zoologists for 4 years, but it's not that I understood everything. So don't ask me. And then here, maybe you already had a look at that. So this is, again, work from the lab of Marco Dorigo in Brussels. Maybe ethically a bit questionable. I'm not sure if they had to pass some ethical check. But the idea is to aggregate robots here at this poor little girl and then pull her some distance away. So the idea is obvious, right? So the individual robot can't pull this, well, lightweight little lady, but still it's too much for one robot. So if they work together, they can actually make it happen. And yeah, I'm not sure if I can maybe jump a little. Whoop. So it's sometime, yeah, okay, so here you see they're ready. And look at, yeah, now it's even the zoom in, and she's not happy. But I was told they had a monitor, a screen on the ceiling, and she was actually watching animations. But yeah, I'm not convinced that that's the best idea for an experiment. Collective construction, there could be some work about drones that I could show you here. For some reason I choose not to. So this is, of course, a really interesting scenario for swarm robotics. Like, we always desperately look for real applications that really make sense. And construction could really make sense, and not just for, like, we fly them to Mars, and then they build structures there to prepare the arrival of some humans. Okay, so there has been some work. So this is again from the group of Radhika Nagpal in Harvard. This is the other science paper where they have this, like they say, termite inspired, but well, talk to me, maybe it's not the best way of selling it. So they built these structures with multiple robots, and it's predefined structures, and then you have problems of coordinating these robots and making sure they do something useful. This is the work of Michael Allwright working with Marco Dorigo again, where you have like smart blocks, so they have an internal state. Robots can change the internal state of these blocks as some form of stigmergy. So in some of the talks yesterday, someone spoke about stigmergy. So this is the communication via the environment, and you can even talk to robots via the building material. And this is then again some of our own work where we do construction with, well, continuous material, which is fibers. We do some braiding, and it's fair, maybe you want to say, like, why would you use mobile robots to braid something and then you call that construction? I mean, that's crazy, right? Yes, maybe it is, but well, one, we can do it, and two, this was the side product of some EU project where we had architects that looked into possibilities of braiding to form, like, actually arbitrary shapes, and they defined some tool chains to basically braid any shape you want. And this is just a quick impression here. So this is like stuff that they could actually really braid. So this is not what they did, but this is some taxonomy of what you could produce. So you can do these tubes, and if you could, well, you can actually scale up, and if you imagine you're scaling up, then maybe you could even build some maybe not houses, but like roofs and some useful structures. So braiding is maybe a nice option. And the architects are crazy about this because you don't have connection elements. Just friction basically holds these fibers together. So slowly I'm getting to the end because I don't want to be overtime and give you some chance to ask some questions. So this is, well, until now I just showed you what people have done. I also want to, like, inspire you or push you or bias you. So I'm not proud of this name, but something to remember. Swarm Robotics 2.0 could be something like you kick the robots out of the lab. So I would like to see much more work. I mean, I'm guilty myself. But I would like to see more work of like real robots doing real tasks outside. So this is again about this project Subcultron, where they did something really useful. And then another hot topic would be this like using swarms as an interface, right? So again, I mean, you can argue, is it really useful or not? But I think it's, well, fun research and also really innovative. So like swarm human interaction or interfaces, that could be something really interesting. And then we have some work on like fault tolerance and increasing robustness, or doing something that we call robust scalability. So I told you earlier that because you have this high degree of redundancy in these systems, well, you have 100 or 1,000 robots, so it seems like it's a robust system. And people have claimed that since, I guess, back in the late 90s or so, that swarm robot systems are robust. But actually it's a lie, because if they have all the same program, for example, then one bug is enough to kill the whole swarm, right? And also for some of these like self-organized, fully decentralized, distributed algorithms, you can also sometimes find a way that just one robot that behaves in a wrong way, maybe by accident, can actually kill the whole swarm, right? So this is things we don't want, and now, again, like in the second wave of swarm robotics, people look into that and try to find algorithms that are actually really fault tolerant, and that's also a fun subject if you ask me. So this is my second last, or almost basically last slide. So I was very happy when I found this paper. So this is in this new journal called Science Robotics. And that's why they have this, again, kind of silly title, The Grand Challenges of Science Robotics. Actually, they want to write The Grand Challenges of Robotics. But this is like a really interesting group of authors that published here in 2018 a paper about these grand challenges. And then, of course, I was very happy to find robot swarms there and some arguments like why future robotics should really look into, well, that's good news for all of us, right? Not just swarms, but multi-robot systems are definitely one of the big things of the future, plus my idea of kicking out the robots of the lab. So try to convince your supervisor to buy expensive robots that actually also can go off-road. Okay, so I'm at the end. These are some of the members or former members of my group who helped a bit with some of these few things that I showed you here from my own group. I'm not really into social media, but the one and only thing I do is Twitter. For some reason I love Twitter, so if you want to know more about our work, you can follow me. Actually, just today we published a paper in Royal Proceedings Interface, I think, about it's a survey paper on constructing living buildings, so living, also with a lot of robotics in there, so this is maybe also interesting for you, and yeah, the book. All right, so thank you, and now I'm curious about your questions.
Yes, Heiko, thank you very much for the inspirative presentations. I really enjoyed it a lot. Yes, maybe it was because of no drones there. We have seen already all videos available in YouTube during these days, so maybe this was the reason. And I'm also happy that you use so many pictures and videos, mainly because of our attendants from industry. They are sometimes complaining about too many equations here.
Yes, sorry, too little equations.
So maybe even you had more pictures and videos than in my presentation. But my presentation was shorter, it was only 1 hour. So maybe I had like
this was, maybe it felt like 2, but this was also one hour.
This was one and a half, no? Or only one?
Well,
okay,
in
so
your dream, yeah.
Then you are better. Perfect. Do you have some questions? Can you try to speak loudly?
The big challenges of field deployment. Well, it's the real world, right? So everything. Let's see. I mean, so the first thing is you need more complex robots, right? So if you look, well, depends. So again, like let's not talk about drones, but if you, well, we had this talk yesterday about this indoor boat, right? So obviously it's a bit easier to build a boat that just works on a pool without wind and so on. If you want to build something that actually, don't know, works in the ocean, then it's more difficult. And similarly for like simple wheeled robots that are supposed to go a little bit off-road, right? It's just a robot that goes across a field or something. It's already much, much more complex than such a little kilobot. So the hardware will be a big issue, and then of course, well, maybe you get something for free, like if you use GPS, you have maybe already good enough localization, depending on what you're doing. Otherwise, yeah, well, you have to think about communication, which is then maybe an issue, like long-range communication. Well, you can, again, use the cloud or the grid, but maybe that's not always the best choice. So I would say, like, there's so many more and different challenges than just doing it in the lab, where it's already difficult to end up with a robust system that does not just happen to work for these 2 minutes when you take the video, right? So it's, I would say it's so much more challenging in almost every concern. Yeah.
Interfacing with the swarm, because we as researchers, we know what with the swarm has to do. We know all the things that we the researchers have to program them to do. But I see that at least this is my perception. I would like to hear opinions about it. Because when it gets time that we are finally able to commercialize some applications, it needs to be dump-proof. So I don't know if there's a lacking of research in that particular part.
So interfacing with swarms, you mean online, like it's running and then you interact with your swarm by like controlling individuals, or?
I do a request like, do this.
Okay, like mission planning or something. Yeah. I guess I'm not really an expert of that, but as far as I know, there's not really much research on like exactly what you mean here, like with a clear application in mind, and like what are really good ways of like making it making swarms accessible for a random person, right? So what I definitely know is that recently there have been a number of papers on like interfaces for interacting with swarms, like all sorts. I mean, of course, you also want to have like the concept that you control one drone and then the whole swarm follows, something like that. Or there have been people looking into like, what is it? Like not a brain scan, EEG or something. So you check the brain waves, and by that you can actually find out at which robot this person is currently looking, and then whatever this person controls goes to only this robot. So there's like a number of really interesting works trying to establish very different forms of interfaces for like human swarm interfaces. Like pushing it a bit more towards applications and making it accessible, I'm not really aware so much. I guess in the drone research there must be something for sure. Maybe you can talk to my colleagues there. Otherwise for like swarms, like ground swarms in the lab, for example, I wouldn't really be aware of so many research. So I guess the answer is yes, it is underexplored, and probably because most roboticists are so much turned on by autonomy. So when they think about a swarm, they want to have an as autonomous swarm as possible, and then they don't even think so much about today I want to solve this scenario, tomorrow another one, and a human supervisor like turning the switch, right? Yeah. So I'm not exactly sure whether I get the question. So this is about how to measure the swarm performance, or how to know when you solve the task. Is that what you mean? Okay, yeah, it's not really that I will talk about that in the next talk, but so if you think about collective decision making, also there you have the problem that at some time you want to have a swarm-wide awareness that the decision has been made, right? So you want to find a consensus, and then once everybody is of the same opinion, or a high percentage of the swarm is of the same opinion, then you would say, okay, now I have maybe not a consensus, but a big majority, and then this would define the collective decision-making process being finished, right? And the problem, of course, if you want to have awareness about that, well, in the swarm, but also in the individual, then you immediately get into the domain where you can only speak about probabilities, right? There's no, well, most of the time, I guess, there's no way of guaranteeing that every single member of the swarm will learn about, we're actually done, right? That's an issue, and certainly one problem you would almost always experience in any swarm scenario, I think, that everybody, like how to guarantee that everybody is aware we are done, or what we have achieved until now is good enough, something like that, if that answers your question. So that's certainly a challenge, and I think there's no good like standard way of doing it. So it will always rely somehow on gossiping and diffusing information through the swarm, but you will always have some that don't learn about it, and you can only like have probabilities of how sure you can be that a high percentage of the swarm is aware we're done, or we are doing well.
Another question? Yes, I have been asked to use mics because of the recording, so if you
Considering the grand challenges you mentioned of taking the swarms outside of the lab, do you think that the contributions towards this will be done by groups working, for instance, only on perception, others only of control, or do you think it's required a multidisciplinary approach?
Okay, so who will contribute most to getting the robots out of the lab?
Not really. It's more like, do you think it's necessary to have these multidisciplinary teams, or if?
Yeah, that's an interesting question. Well, the problem is I haven't done it, so I don't really know what the problems will be. Again, yeah, this relates to the first question we had, like everything probably will be a problem. So that sounds like it should be, yeah, you want to have an expert for everything. But, so like after having done quite some robotics in the lab, working with real robots, I would say your biggest problem will be to keep them working. So the biggest contribution will be from the technician to repair them, to check what's the problem, and making sure you can continue doing your experiment. But yeah, I guess sensing will be a big problem, getting good enough data so that your robots actually have a chance to perform in some way intelligently. You know, it's the garbage in, garbage out problem. So if the sensor data is not good enough, you won't get something. And I can only speculate. I'm tempted to say like control theory maybe will not help super much, but maybe just because I don't like it so much. So I don't know. But the problem will be dirty, sandy robots stop to work, and maybe, yeah, the actual scientific aspect will not be the biggest player anymore.
Antonio?
So in one of the first videos that you have shown, there were these ships.
Yeah.
And so, I mean, if you take alone, a ship is a complex system, okay? It's a
definitely
legged system and so on. But seen from far away, they look like a swarm. But where is the switch? And is there anybody who is doing research in this? So when is more, for example, questions related to this. When is more useful to look at them as worms, and when is more useful to look at them as mechanical systems? And it depends on the number, depends on the task, depends on, and there is a region in which we should look at them both as worms and separate mechanical system interacting.
Yeah,
so
yeah.
you see my point, no?
Yeah,
So
yeah.
in this part in the middle,
Right.
so I think I see something in this.
Right,
part.
right. So, well, if you allow me to rephrase the question a bit, so the question for the video would have been like, for how high should this drone fly to say this is a swarm, this is an individual sheep? Well, to try to avoid talking about stupid definitions, well, it relates a bit to the question of how big is a swarm, right? So my answer to that would always be, it just depends on the methods. Like 2 or 3 robots can be a swarm if the methods they apply are scalable. So they use local information only and so on. Although, like from the outside, you wouldn't really see a difference maybe. So I definitely agree that there must be some interesting transition regime when you go from, well, single robot to like robot teams where you have all-to-all communication, like this, like RoboCup style, like you have negotiations and like everybody shares information with everybody else. So that's certainly useful if you have just a few robots and maybe you want to make use of the technology we have, so you do that there, but that doesn't really scale. So I guess the transition is in terms of the methods, and that means something you have to, well, that means you have to look into the robot. So the drone wouldn't get the answer by flying higher and higher, because maybe they would behave in the same way, but the one system communicates like hell, and the other one has like a scalable communication scheme, right? And if they do it well, you won't see a difference from outside. So I guess the question is like at what, and that's the interesting research questions probably, so at what time should you make this transition in your methodology? So your robot team gets too big because it doesn't really scale perfectly, so you should switch to something that is a bit more decentralized or fully decentralized. So you could think of, like, don't know, having some overlay networks that you can still do some of this team game, right, talking to each other, like everybody talks to each other, at least within that overlay network, and then you distribute something to like a decentralized part of the system. But yeah, I mean, it would be fun to try to do something that actually incorporates that transition, right? That you start from single robot, then team of robots where they talk to each other, all of them talk to each other, and then you scale up, and then at some time they slowly switch to, okay, maybe I shouldn't send a message to everybody anymore, because then the system will, well, there will be some bottleneck somewhere. Yeah. So that's, yeah.
The sensor limitation, the power, it's a matter of this. How they really are built in terms of sensing, of actuation. What is the outreach of their actuation?
Yeah. So the idea was in biological systems they do that. So if you have, so I know some papers about like construction behavior in wasps, social wasps. And there, biologists actually observed that. So you have, like, this is about task allocation, a bit related to what I've showed, that if you have just, like, these wasp colonies grow during the year, right, they start small, and when they're small, everybody's a generalist. So everybody does everything, like collecting water, collecting, like, wood, and they build and everything. But then at some time you also observe this transition that they start to do actually some task allocation, that not everybody does everything, right? Because it's more efficient at some point once you reach a certain group size. So yeah, it would be maybe worth looking into that, because who knows, maybe natural evolution found a good way of making this transition, right? So it could be really interesting to look at that. Thanks.
Okay, so let's keep the rest of the questions for the second part. So now we will give you 2 hours break, so you can refresh yourself and be prepared for another intensive presentation. And I will ask our student presenters, who is the first?